pTable is an example of a database app. It's an application that takes data and makes it more visual so we can start to ask interesting questions. So for example, in this database here, obviously the colors tell us something. They tell us basically the classifications of the elements. So if we want to look at the alkali metals, we can see them over there. If we look at the alkaline earth metals and so forth, we can see even more information and so forth if we click into it. But it's very useful in terms of making basic comparisons. So for example, perhaps the most important property of elements are their radius. So if we look at radius right here, we'll see the distance from the nucleus, the center of the nucleus, to the valence electrons. And we can see that elements like cesium, rubidium, potassium, this family is relatively large. In other words, cesium with 298 is much larger than radon with 120. Or sodium with a radius of 190 units right here is going to be much larger than argon. Now this can help us as we start to look at other properties. So we start to see this periodicity or repeating pattern, just like there's a period at the end of any sentence. So a periodic table has repeating patterns, a periodicity to it. So let's say we look at ionization energy right here. And now students can go back and forth and say, oh, wow, I noticed that those elements which have relatively large radii have relatively low first ionization energy. And of course, then you could lead into a discussion on why that is. In other words, that those elements there where the valence electron is very far from the nucleus, those electrons are not bound as tightly as the ones which are close to the nucleus, like in the noble gases here. So if we look at this, the ionization energy in the noble gas is very, very high. We can see that helium extremely high. It's very difficult to ionize helium, very difficult to remove an electron from it. And that's because its radius is so small. So it has a very small radius, and therefore it has a very high ionization energy, a lot of energy required to remove that outermost electron. Similarly, if we look over here and we can see that cesium, which has a very, very large radius, so the electrons are very, very far from the nucleus, relatively speaking, has a very low ionization energy. We can see here that is one of the lowest ionization energies just looking at this heat map. Francium being equivalent there. They're about both 380. So the point being is that we can start to see relationship between properties. We could take that on to other important properties like electron affinity, the tendency to gain an electron, etc. We could also start to look at properties that are more noticeable, things that are more easy for an untrained chemist and so forth to conceptualize. For example, let's say we want to talk about melting point. So click at melting point, and we can see this heat map right here, and we will again see some periodicity, some repeating patterns, like this family over here has very, very low melting points, whereas this area right here in the metals has very, very high melting points. And so let's say we wanted to say what has the highest melting point, and so we can just drag across like this, and it's going to start to change the colors, and it's going to leave us with those things which have the highest melting points. And you can see that tungsten and carbon, and not surprisingly, those are two elements that have been used for light bulb filaments because they can glow, they can give off light without melting. And so we can start to see a relationship between the physical properties and their application, and it makes it very easy to do with something like this. We can also start to look at correlations, like correlation, let's say, in terms of their conductivity. So if I look at conductivity, we can see that, oh, certain elements are like copper, silver, and gold are highly conductive. Not surprisingly, electric circuits are generally made of copper because even though it's not the most conductive, it's cheaper than silver or gold. And then if we started to say, well, how about does that compare with that's thermal conductivity, actually. So we look at thermal conductivity and then we compare it with electric conductivity. We see that the patterns are almost identical. In other words, electrically, these things conduct currents very easily. And if we look up here thermally, we can see that they conduct heat as well. So now we can start to see that perhaps by the comparison of these two principles, the underlying idea is that something that is contributing to their thermal conductivity also explains their electrical conductivity, or vice versa. So we can start to see patterns in the data. Let's say you wanted to look at just the naming conventions. You notice that most of the elements have names where the elements symbols match their name. But if I look under discovery here, let's say we went back in date, like way back here, and so we go back to some of these early ones, and we'll start to see that in some of these early ones here, like that have been known for a long time, like tin. Well, SN doesn't seem to line up with tin, or SB doesn't line up with antimony, or PB doesn't line up with lead, or HG with mercury. And that's because these have been known for a long, long time, long before English was the language of science. And so things like gold and mercury and silver and so forth have been known since time immemorial. I mean, way back. And as a result, that their names are probably in another language, primarily Latin. So we can see the relationship here between naming and the symbols and so forth that are given to them, and the history. So uh, again, there's so many things you can do with a dynamic periodic table, and that you can't do with a paper one. And just like there's so many things you can do with a dynamic database of any kind, you can't do with a static or paper bound one here. Let's just look at one more thing here. That would be in terms of abundance. Let's say you're doing a geology lesson or earth science lesson. Look at abundance. Here's the abundance in the crust. So we see here, wow, in the Earth's crust, looks like oxygen takes up almost half of the Earth's crust. And that's kind of hard for people to realize, because you think oxygen is a gas. Well, oxygen obviously complexes with silicon dioxide, SiO2, is sand. It's dirt. It's the main thing which is going to be in most of your rocks. Aluminum, iron, calcium, and so forth, these ones here constitute the other major elements. And so you can look at this and say, wow, this really represents the Earth's crust. How about in terms of the universe? Look at the universe, and we kind of go, oh, a very different story. The abundance in the universe. Most of the known universe, most of what's considered normal matter, is hydrogen with less helium. Again, helium, coming from helios or sun, was actually first discovered in the hot sun. And hydrogen fusing together to give you helium is the nuclear reaction, which of course gives us sunlight and starlight in general. We notice all the rest of the elements are extremely small in terms of their percentage. If you look at a logarithmic scale, we can see, however, that they actually show up. And that's simply what we're doing is we're basically showing things, even though their orders of magnitude different. We're plotting them like on this logarithmic scale, so we can actually see relative values. This is a linear scale showing that almost everything is hydrogen and helium. But if we plot it in a logarithmic scale, we can start to see the relative abundance of everything else. And so we can start to introduce a math concept as well, in terms of the difference between logarithmic and linear scales. So again, the key thing here is just to understand how a dynamic database gives you so much more functionality than just a static database. And many apps are coming out to analyze data of many, many different sorts. This is just one particularly valuable to chemistry teachers.